Hello, my students and viewers, chemistry learners, students of higher learning all over the world. Wherever you are watching this video now, I send you a greeting. This is a topic called the integrated rate law for first order reaction. It is under chemical kinetics. I have uploaded a video on chemical kinetics, uploaded a video on rate of reaction, rate law, rate constant, and also a video has been uploaded on order of reaction. Okay, so now I need to take each of these kinetics serious, most especially first and second order, and how you can have a general formula for first order, second order, third order, zero order, fourth order, as the case may be. Okay, but the most type of order of reaction is first and second order type of reaction. So, but you can generate a formula for third order. Okay, from the integrated rate law just by simple integration. Okay, or you fourth order, fifth order, as the case may be. But also you can generate it from a general formula that will be given to you later, though not in this video. This video is just about generating an integrated rate law for first order reaction. Okay, any first order, either it is generated by experiment or generated by any form. Once it is a first order reaction, how do you get the integrated rate law? Okay, I am going to first of all be explaining briefly. You can go back to my last video, past video, you see order of reaction. If I'm in this video, since I'm talking about first order, if we take this as a first order reaction, this is actually a first order reaction. Okay, I have done a video that talked about rate expression. You can also go there. You need these videos on rate expression, rate law, order of reaction to be able to derive the integrated rate law for first order. So I will not be talking about that here. You are expected to go back to those videos and watch in this YouTube channel. Okay, if you have not subscribed, do that, share to others, and you will get knowing chemistry the better. Now, let's go. If this is a first order reaction, okay, how do you know? Because the rate law rather, okay, will give us this. So, but let's go this one. Let us say that rate expression, okay, rate expression, which is rate, is equal to rate law. Let's do it this way for a learner to understand. For the rate, in terms of the disappearance of A, you have minus delta to the concentration of A, okay, over dt, okay, is equal to the rate law. The rate law is a function of the concentration, which is Ka raised to the power of 1. The stoichiometric coefficient is 1. So I have been able to say rate is equal to rate law. And so from here, I want to bring the two concentrations together so that I'm going to have delta A of this. If this is to come here, this comes here, just a simple cross multiplication, this coming here, why this come here. So I'm going to have this, okay, then is equal to, I'm going to have k dt. I hope you understand that. And from there, I'm going to, this negative will come here, I'm going to have is equal to minus k dt. I hope you understand this. Okay, I hope you understand this. So if you integrate both sides of the equation, so you can see, if you are going to integrate both sides of the equation, you are going to be having, you integrate here, you also integrate here. That means integrating it will give you this. This is the sign of integration, okay, at a particular concentration, at a particular time, and also at a particular initial concentration. What are you integrating? Remember, you are integrating this, which is this over this. Okay, that is what you are integrating, and also integrating the right hand side of the equation at a particular time t and at a particular initial time t0. Okay, this minus can come here, then I'm going to have my k dt. Okay, I hope you understand that. So this also can also be written as this. Okay, please, this video, as you watch any of my video and it inspires you, it helps you to know chemistry better, please make your comments. And if you discover any error in any of my teaching, you also make comments so that I can look at it and see where I need to make correction. Okay, so you look at this. As you integrate it, you can leave this in this form, that 1 over the concentration of A to D to delta the concentration of A is the same. Okay, I've not done anything strange here. Is equal to the integral of t to t0. That means if t at a particular time t and t at a particular time 0, I have my k dt. Okay, do you know that in integration, in integration, if the integral value of 1 over s is equal to ln s. I want to bring it up here now. So it then means that integral value of 1 over this will give me what? Ln the concentration of A. So I am bringing it up because I am having the integral of 1 over A. So it means that everything here will turn to ln A. That is what it means. Okay. So in a nutshell, you are starting from here, ending here. That means you have. So I can say that this will give me ln concentration of A. Okay, as this, let me call this 0, this at a particular concentration at a particular time. Okay, then I'm going to have also ln concentration of initial. Okay, this will now be my initial, taking this as my final. Okay, then is equal to, if you integrate this, you are going to have minus kt. Okay, so this is the integral rate law for first order reaction. So in a nutshell, you can also say that ln, the concentration of A can be any compound, please understand, or the ln of the concentration of A at a particular time t, minus ln the concentration of A, okay, at the initial concentration, okay, is equal to minus kt. Okay, do you know that if you are going to raise each side of the equation to the exponent e, each side of this equation, if you raise it to an exponent of e like this, okay, the equation will be like this one now. Okay, the equation will just turn to e, okay, raised to the power of ln A, okay, is equal to e raised to the power of ln A naught. Okay, this is 80 at a particular time. Okay, all minus kt. This is what, if you are bringing in an exponent. Okay, this is what will be coming out. Okay, I hope you understand. Okay, so it then means in the end you are going to have concentration of A at a particular time t is equal to concentration of A naught, that is the initial concentration of the reactant, okay, times exponent, okay, raised to the power of minus kt. If you solve this, it will give you this. So this formula is the integrated rate law for first order. This is also integrated rate law for first order. For first order, any of them can go. You can use them for calculation and you are going to get an answer. And also, this is very important for you to know because this is what you are going to be using to plot your graph. I will come to that later. This video is just to know how to derive the integrated rate law for first order. Okay, how you generate it to solve questions. I will be solving questions, I mean live questions later, and also I will develop videos for that. And I will also be using it to solve some graphical questions that demand graphical answer. I hope you understand that. Okay, for first order, second order, and the rest of them. So please kindly follow what I am teaching, and I am sure I can beat my chest that you will not be lost. Okay, so we want to look at the half-life of first order reaction. Okay, half-life of first order, just the way we have integrated rate law for first order, the same way we have half-life for first order. First of all, what is half-life? Half-life is the time taken for the initial concentration of the reactant to reach half of its original value. Okay, so let us recall, please note what I am doing here. Okay, recall the integrated rate law. Okay, recall, what are we recalling? Recalling integrated rate law for first order reaction. Okay, here I'm using this because this is what you can use to generate the half-life for first order. Okay, I believe you can still know, you can still remember this formula, just the same formula I derived just now. So if I say this let T is equal to the half-life. Do you understand? And because we say half of its original, this is the original concentration or the initial, okay, value, okay, initial concentration of the reactant to reach half of its original value. I come again, we say half-life is the time taken for the initial, this is the initial concentration of the reactant to reach half, to reach, so in that means that I am going to be saying that let this reach half now of its original, okay, value. That means let this one now, okay, reach half of this. Do you understand? Do you actually understand? Let this become an half. Do you understand? That means half of its original value. I come again. The time taken for the initial concentration of the reactant to reach half of its original. So in that means I'm going to be saying this A naught divided by 2. Do you understand what I've just done here? So if I am putting this, let T be this and let A be this, okay? Substitute. Let me call them equation. Let me call this equation 1. Let me call this equation 2. Okay, substitute. You are substituting what? Equations. You have two equations here, this and this. 2 equation, let me just say equation 2. Okay, we have two equations here, please understand. Okay, into 1. Let's do that now. Look at what is going to come out from it. Okay, what do I have here? A. So I'm going to put this is equal to, what do I have here? I have my A naught, okay, then multiply by what? The exponent. Okay, k. What is my t? My t is half. T half. Do you understand now? Okay, and if you do thorough calculation in mathematics, this will cancel out. Then you will be having 1 over 2 is equal to e raised to the power of minus k T half. Do you understand what I've just done? I hope you actually do. So if you take lean, if you take lean, okay, to both sides of the equation, okay, that equation, let me say 3, equation 3, you are going to be having ln 1 over 2 is equal to what now? You are going to be having ln 1 over 2. So here, putting ln here is equivalent to removing this. I hope you understand, because what you have here, okay, is if you are bringing in lean here, a mathematician will understand what I'm saying. I believe you are a chemist and you are a learner in chemistry. So just understand that this exponent, okay, is a form of lean. Okay, that means bringing in lean here, it will cancel out, remaining what now? Minus k. Okay, minus k what? T half. In this case, you shall be making T half the subject of the formula. Do you understand? And if you are making T half the subject, you are going to be having T half is equal to what now? Minus ln half over what? K. And this is equivalent to ln half. This one will come up here. I hope you understand that. Raised to the power of what? Minus 1. Okay? Over k. And this actually means if this thing is solved, this will now be ln 1 over 1 over 2 over k. This will, I hope you are seeing what I'm doing. Okay, let me ensure you see what I'm doing. Okay, now that means you shall be having ln 2 over k. That will give you the half-life. Ln 2 over k, that is the answer. Or ln 2, if you press in your calculator, give you 0.693 over k. I know many don't know why they see this formula often in a chemistry textbook, and they just use it to solve questions. This is how it is being realized, where k is our rate constant, which can be gotten from the question, a calculation question given to you, or from any other means. I hope you understand this effectively. Okay, this is just to tell you how you can derive the integrated rate law for first order reaction and the half-life for first order reaction. If you know you understand what I've done, I want you to share the video and follow up my YouTube channel, so that whenever a new video comes up, you can learn and share to others. Okay, thank you very much. And if you do understand, please make positive comments in my YouTube channel at the comment option, okay, below. And also, if you do not, you seems you are understanding, but you are not getting it well, listen to the video again. Listen to it again and again, continuously, constantly, and you will get this. Thank you, and God bless.